Well, my friends, here we are. It's time to learn about the quantum properties of the electron, its wave-like properties, and things are going to get a little weird, as you'll see, not only because I'm going to show a video inside a video this time, but because understanding the wave-like nature of the electron is strange. But hopefully we'll teach you the material. Hopefully you'll have questions that we can then answer. And it's certainly interesting to me, and hopefully it will be to you. All right. So this is lecture outline number 8. This is Roman numeral 3, part 2. Now we're talking about the wave-like nature of matter. And particularly we will see that the wave-like nature of matter in chemistry is really only important for electrons. And things smaller than electrons, but in chemistry, it's pretty much the electrons that are the smallest thing. So we'll start with, for an electron with a given amount of mass, mass being a particle-like property, the wave-like nature of a matter, the electron, is significant. What we will see is that if you have an electron source and you do the double slit experiment, which for light waves produced an interference or diffraction pattern on a screen, you do the same thing with electrons and you also get an interference pattern or diffraction pattern. Wow, so cool. All right, now what I'm going to attempt to do next is we will watch a video about this.
If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern.
Never gets old.
We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Particles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Pretty trippy, eh? So let's cover a couple things here about this. So first off, what is an electron? An electron has particle-like and wave-like properties, so it has both of these, and it exists in what's called the wave-particle duality. Okay, and then when one single electron goes through at a time and creates an interference pattern on the wall, what is interacting, what is interfering like the waves? What is going through one slit and what is going through the other slit? It is the probability of the electron going through each of the slits. So, I know, right? So, when you have an electron source, you have double slit experiment, you create an interference pattern. Question is, what is interfering with with itself, or what is interfering? And in fact, it is the probability, 50% probability of electron wave function and we won't say too much about the wave function other than the wave function describes or can be used to describe all the properties of an electron. It's not a wave, it's not a particle, it's a wave function. 50% of electron wave function probability. Goes through the slit on the left. The other 50% goes through the slit on the right, and it is the probabilities of the electron going through the slit that interfere with each other. So, this is weird. The probabilities interfere, and in the video, when they actually put something to tell which slit it goes through, there is no longer a 50-50 probability that it's going through each of the slits. Once you know, once you observe it going through one of the slits or the other, then there's only a 100% probability of it going through, let's say, this slit, and therefore There is no, well, and then either it didn't go through this and there's a 0% probability. Either way, you know it goes through one of the slits. There's no probabilities to interfere, and you get particle-like behavior only, which is 2 single bands here. Okay, so what do we have to know? Based on this, electrons exist as probabilities. And from now on, when we talk about where the electron is, we will talk about probabilities of where an electron is, and that's what orbitals will be. That's coming up. Okay. All right, anything else we have to say about this? Nope. So let's go through a couple cases. Okay, this is 4 drawings of the double slit experiment. We have a shooter of some sort. We have a double slit. And we have a screen. And the question is, what kind of behavior will we see on the screen depending upon what we shoot through? So shooter here, this shooter is going to shoot wavelengths of light. And that's going to look like this. Some of the wavelengths will go through the top slit. Some of the wavelengths will go through the bottom slit. Those 2 wavelengths will interfere, and on the screen they will produce an interference pattern. And I'm not sure which of these is the actual bright and dark spots. The key thing in this drawing is there are bright and dark spots, and you can see that there's an interference pattern. Also called a diffraction pattern. Okay, so that is straight wave-like behavior of light. We're used to that. We now know that light is, and all electromagnetic radiation is or are waves. Now over here, we're going to do the same setup, except this time we're going to shoot electrons one at a time. And electrons one at a time have probabilities, and those probabilities have wave-like properties. Probability is a wave-like property. So whereas over here the wavelength was an actual wave of light, here it's a probability wave. And that's the same thing, and those probability waves interfere and create an interference pattern. Why? Because the wave-like properties of electrons are important. Okay. So now down here, we'll do a couple other examples. This one's going to be a proton shooter. Protons are going to be mass. They're going to be about 1,800 times more massive than an electron. What we will see is that protons, the wave-like nature of a proton is not important. It has too much mass. It only acts like a particle. And there is no interference pattern. There are only 2 lines where the particles go through. And let's see, atom. Because any atom is going to be heavier than 1 proton, except a hydrogen atom, but any other atom, no interference, straight particle-like behavior. And there's 4 examples of the double slit experiment and what you would see on a screen. Okay, next thing we want to cover is that how to calculate the wavelength of matter. and specifically the wavelength of an electron, although this is a completely general equation. So the wavelength of any matter is going to equal Planck's constant over mass times velocity. We're familiar with Planck's constant by now. We know that when things are in units of energy that are joules, the mass must be in kilograms, and velocity must be in meters per second. Now, as an example, what is the wavelength of an electron traveling at 2.2 times 10 to the 6 meters per second? Pretty fast, very fast in fact, but still slower than the speed of light. The velocity of an electron in the hydrogen atom, to a good approximation. This time we'll write wavelength of an electron. Planck's constant divided by the mass of an electron from the previous slide and on your conversion equation sheet, 9.1 times 10 to the minus 31 kilograms. The speed that we've been given for the electron, type this in. I get 3.31 times 10 to the minus 10. And these are units of meters. That is an extremely small distance. However, if we convert this into nanometers, we get 0.3 nanometers. However, 0.3 nanometers is approximately the size of an atom. So for anything bigger than an atom, this is not important, but for the atom it is important. The wave-like nature of the electron is important for an atom, and so the approximate size of an atom is 0.3 nanometers. That's going to mean that the probabilities, and essentially if you're talking about an atom, you can only talk about where the atom is, where the electron is in the atom, in terms of probabilities. And so that's where we'll pick up on our next part of this lecture outline, is how do we understand electrons, where they are in atoms in terms of probabilities.